So let's look at 14.1. 14.1 really is the same sort of idea here. We're going to be using traces to help us identify different graphs. But now these aren't like a whole bunch of ones we're going to make sure we memorize. It's just a tool to help us kind of tell different things apart. So we'll talk about these sort of in terms of functions of two variables. And then we'll talk about level curves. But like, spoiler alert, a level curve is just a z-trace. They're exactly the same thing. So we're going to just be using not even all of the traces, but just those z-traces in order to help us identify shapes. If you did the Tuesday activities, then you got to learn all about level curves. If you didn't have a chance to do that, not this week, but next week is catch-up week for Tuesday activities. So if there's any that you wanted to go to but you couldn't get a spot in, you can come next Tuesday and do any of the 3 activities that have happened so far. There are still some spots for tonight. It's going to be super fun. You should come. By tonight, I mean tomorrow night. There's not any spots for top night tonight. Sorry, I misspoke. But there are spots for the 4:40 Tuesday session tomorrow. Okay, so what does a graph of a function of 2 variables look like? Before, if you had a function of like one variable, f of x equals x squared, f of x equals x squared, what does the graph look like? Parabola, right? F of x equals x squared. So there was just one variable, but I graphed that in 2D because I had an x value and then the output value. So if I have a function of 2 variables, x and y, right? So it's a function of x and y. So in order to figure out the function value, I have to pick both an x value and a y value. So if they're both 0, the function value is 0. If it's 1, 0, the function value is 3. 0, 1, the function value is 0. 1, 1, the function value is 4, and so forth. You see where those numbers are coming from? Plugging that x value and that y value into my function and just calculating it out. And so for each of these, right, I can go to 0, 0 in my domain and then go up to a height, a z value of 0. So that's my first point. 1, 0, 3. So I go to the point 1, 0 and then go up a height of 3. And that's my point. 0, 1 was also 0. Really along this whole line will be 0 when x is 0. 1, 1, we went up to a height of 4 and so forth. So I can figure out for each of these what my height is going to be. And I have to fill that in sort of for all of the points in between. And I'm going to get this set of points above here that shows what this is going to look like. Right? I picked some random function, so it's hard to see. But if you ever want to kind of picture what these look like, go over here to our good friend GeoGebra, and we can just put it in. So I'm going to do that real quick. So I'll just put in x, y. Oh, sorry, let me actually do a z equals. Z equals xy plus 3x. Oops, that was a 3 squared. Now it's a 3 to the x. Come on. And so that's what this surface looks like. It's actually also one of those hyperbolic paraboloids. Move it to my positive axes. So we can see sort of along there, along that green axis, it's 0. That's where x equals 0. And then I'm getting the rest of the surface from there. The reason it looks like that hyperbolic paraboloid, but it's sort of twisted some, is because of that xy term. Those xy terms are what kind of twists your different shapes around. Okay, so I wasn't going to be able to get some picture that looks like this just by drawing dots, but I wanted to give you an idea of how we actually get these points on the surface. So let me go ahead and just pull this in. Stop twisting. Stay. Okay. We'll pull this in here. Save the photos. Come on. Okay. So we've seen some of these before. What is the first one going to be? I'm going to rewrite it as z equals, since it's easier to picture. Z equals 3x minus 2y plus 1. A plane, good, right? We should think of this as a linear function in x, y, and z. So the x is only to the first power, the y is only to the first power, and the z is only to the first power. It doesn't matter what side of the equal sign they're in, because you can just move them all around to make them plus or minus. And if you have x only to the first power, y only to the first power, and z only to the first power, with a constant in there, that's always going to be a plane. And how about the next one? All right, so before I thought about planes as sort of this equation. Now I'm thinking about planes as just a function of x and y. I can take either perspective there. The next one is I'm hearing some cones, half cone, agreement, disagreement. All right, again, think of it as a z equals. And if you don't like the square root, you could square both sides, but you have to remember you're actually adding extra things there, because before z was only the positive square root, so it had to be greater than or equal to 0. So it is going to be that half cone. Could I have written the entire cone as a function of x and y? Could I have written the true cone as a function of x and y? This word function really should mean that there's only one output. So it's like there should only be one z value for a given xy value. So if I had a true cone here, if I had this true cone, then for a given xy, there's two different values. There's the value on the top part and the value on the bottom part. So that's not a function, because functions can only have one value, right? It's like when you're doing that vertical line test in like pre-calculus to check if something is a function. So this wouldn't be a function of x and y if it was the whole true cone. I couldn't write it as a function. Okay. Function should only have one output per input. Okay. So again, when I'm trying to figure out sort of these more complicated functions, I'm trying to visualize their graphs, I'm going to be use what's called level curves. But level curves are really just those z traces. So we've got our good friend. Ooh, I switched them around. Let me switch it back. I have to do something silly here. We've got our good friend, the paraboloid, and now it's just a half cone. And so we're going to look at those z traces again. Where's that? So let me pull in that. We already did that earlier today. Right. I don't want that to go away. Oh, come on. Okay, there we go. Oh, what? What was that? How did that happen? Okay. So let's see how we did. Pretty good, pretty good. I can pull that right into here. So it's a little different now because I have this square root. And so I would just have k equals the square root of this. And so now I really am only getting the top halves on each side. So on one of these, I'm seeing those circles of radius root k. And on the other one, I'm seeing those circles of radius k. Now, the thing that we're going to do that's a little bit different in this section is instead of trying to draw all of these curves kind of straight up, I'm going to take all of those and I'm going to squish them down into 2D. And I'm just going to try to draw all of those level curves, all of those traces in the XY plane. So here, at k equals 0, I get that point. And I'll label that 0. K equals 1, I get a circle of radius 1. K equals 2, I get a circle of radius root 2. So I have to bring it in a little bit. It's going to be somewhere around here. And I'll label that one as 2. It's a circle of radius root 2. K equals 3, I get a circle of radius root 3. I'm labeling it with the K value, so I'll label this one as 3. And then K equals 4, I get a circle of radius 2. Pretend I drew a circle. That's that. Now, on the other hand, I am actually getting circles of radius K. So when K equals 0, I get a dot. K equals 1, it's a circle of radius 1. K equals 2 is a circle of radius 2. K equals 3, I can do a little bit better than that, is a circle of radius 3, and K equals 4 is a circle of radius 4. So what are we seeing? What are sort of the differences here? I'll let you think about that as I pull you in some slightly better pictures. So I always got to go back and find them. I took them a while ago. So think about what's different between these two shapes. Where did they go? Here we go. This one. And I'll erase the other stuff in a second. This one. Okay, so here's those nice better versions of the shape. How could these help me identify the difference between those two pictures? This one, my circles are evenly spaced. What does that tell me about sort of the edge of my cone? Versus this one, they're getting closer and closer together. What does that mean? Good, so that's kind of my linear change versus the parabola, where a parabola, what's kind of different? Is it why? It's not a linear change. It's getting steeper and steeper as I go. So closer level curves means you're getting steeper and steeper. You're changing heights faster and faster. Where if they're evenly spaced, your height is changing at a constant rate. So what are these level curves reminiscent of? Anyone see these in like a physical way printed that you like buy? Yeah, they look like topographical maps. Right, has anyone seen a topographical map before? Right, the lines on a topographical map are exactly telling you where all the level curves are of like the surface of the earth. Right, so I'm slicing that, I'm thinking about where I have constant elevation, and then I'm drawing a curve of constant elevation, which is just that constant z value. So this is right here, I have this map of Acadia National Park. In purple here, what are these sort of purple concentric circles? How am I viewing that? That should be a mountain, right? So these concentric circles, it could also be a pit, a hole. Yo, give me my 2 minutes. We got this. I'm gonna tell you about Acadia for a couple minutes and then I'll let you go. So, right, that purple mountain right there, that's Cadillac Mountain if you've been up to Acadia. You can see that there's some really steep trails. That's when the contour lines are really close together. And then over in the flat section, I don't have as much contour lines. So it's nice and flat. So when we're talking about using level curves, we're really drawing like a contour map of our surface and then trying to use that to build up what that shape is. Okay, next time we'll go through and talk about domain, and then we'll get to match all of these surfaces with their equations. So look forward to that. See y'all then. If you come to Calc Night tonight, I'll be there with pizza.
I'm a little confused about
All right, let's start here. We're going to finish talking about our functions of several variables, that's section 14.1, and then we'll move into 14.2 on partial derivatives, and we'll see some things about partial derivatives. And then we'll continue with the rest of chapter 14 this week. So the topic that we're going to start with is finding the domain. Finding the domain of a function of two variables is a lot like finding the function of the domain of one variable. But when I have the function of a domain of one variable, right, there's only one input. So I just get some subset of that real line, usually some interval. Here, when I have a function of two variables, I put in both an x and a y. So now my inputs are all of R2 potentially. So instead of just looking at sort of a one-dimensional possibility for our inputs, we have this two-dimensional possibility. So we can get weird shapes as our possible domain. But we're still going to have the same basic thing. Sorry, I didn't delete this before. You don't need to answer in a Slido. We're still going to have the same basic rules for things that you're not allowed to do for that domain. So what are the bad things for domain? What are we not mathematically allowed to do? Anyone think of any of them? We can't divide by 0. We can't divide by 0. So if you have some number over 0, boom, sad face. We can't take the square root of negative numbers. So square root, is there any other roots I can't take of negative numbers? Can I take the cube root of a negative? Can I take the fourth root of a negative? Fifth? Sixth? So right, we can't do even roots of negative numbers. So if I have some roots and there's a negative under there, again, I'm sad. And then the last one, you can't have a non-positive number inside a logarithm. So negatives and 0 are both bad if it's inside an ln. So ln of negative or 0. That makes us sad. So when I'm looking for the domain, I'm looking for these sort of common domain restrictions. There's another set of functions that also have some domain restrictions that we're not going to worry about too much. Has anyone ever seen some other functions that have domain restrictions? The tangent, good, because it's sine over cosine, so that when that cosine is 0, so that's sort of a special case of that can't divide by 0, 1. And then there's a whole family of functions related to something like tangent. Piecewise functions could also have domain restrictions. Inverse trig, all of those inverse trig functions have really restricted domains. Because in order to take an inverse, the function has to be 1 to 1, so we restrict the domain, so the original function's 1 to 1, and then we can take the inverse. In particular, that's where all these, bug up there. That's where all these things come from. It's just a dragonfly. We're fine. Don't worry. Okay. So in my first function here, Is there anything bad that can happen? Is there any square roots? Any logs? Any dividing by zeros? Any inverse trig? Everyone's like staring at the dragonfly now. Way to go. Is there any of those? Nope. So the domain is all. We can't just say all real numbers here because we need to represent the fact that x can be all of the real numbers and y can also be all of the real numbers. So I have two sets of those real numbers. So I would say it's all of R2. One copy of R for all of the possible x's and another copy of R for all of the possible y's. How about the next one? What is the domain of 3x plus 2 over x minus 2y? Here I need to make sure the denominator is not 0. So I need to make sure this one is not 0. So I say x minus 2y is not equal to 0, which when I'm picturing graphs of functions in 2 dimensions, I like to think about y equals because I know how to graph those the best. So I'm going to move some stuff around and say y is not equal to 1/2 x. So if I was to draw this out, I'm going to have sort of my bad line here, y equals 1/2 x. I'll just kind of draw something in and label it y equals 1/2 x. That's where we can't have our domain. So the domain is everywhere else except for that line. So it's all points in R2 except for where y equals 1/2 x. So you can kind of picture if I colored everything in and then I just erased right along that line, that's what that domain would look like. Okay. So go ahead and see if you can find the domain of this function. I want you to try to figure out what it is algebraically. So like up here, when I just said x not equal or y not equal to 1/2 x, that was my algebraic expression. And then also try to graph that. So it'll take about 2 minutes for you to work on that. I'll come around and see if anybody has any questions. Maybe I'll try to help this dragonfly find a good place to go live. You're so loud. Mommy. Okay, come on. Carefully. Is it on me still? No. Okay, I tried. So how are we doing with this? As we're getting started, what are we seeing? There's really two different things going on. There's a square root, and it's also in the denominator. So the stuff under the square root has to be bigger than or equal to 0 because it's under a square root, but it can't be equal to 0 because it's in the denominator. So you should have a strict inequality. Uh-huh.
So I did like 2 problems on 12 and the grade automatically put in. Will that be updated?
Yep. As you work on it, it continuously gets updated. You can't split the square root over a plus or minus. What should we get here? Thinking. Anyone have a graph I want to share? If you move this over, what kind of graph, like curve does that look like? Move the 4 over, what does it look like? It should be an inequality, a strict inequality. If that was an equals, what would it be?
This way, square root.
Just in 2D, not in 3D.
Isn't the inside has to be like?
Just the inside has to be strictly positive. Yeah, so there's not any square roots anymore. Remember, you can't split a square root over the plus. Good. Okay, let's see what we have here. So when I see this, I say, okay, there's something under a square root, and then I'm just gonna pull out this piece that's under the square root. And because of the square root, I'm gonna say that has to be greater than or equal to 0. That's just my first like half of a step. And then I'm gonna say, oh, well, it's also on the denominator. And so therefore it can't be equal to 0. So that I have to update this and say it has to be strictly greater than 0. So I get that x squared plus y squared minus 4 has to be strictly greater than 0. So now I want to kind of move this stuff around so I can see this as a shape that I'm kind of used to so that I can graph it. So when I see an x squared plus y squared added together, I'm like, ooh, I like those to be next to each other. So let me move the 4 over. And now maybe I can recognize what this shape is. And I do it correctly. Add that 4 to both sides. So I get that x squared plus y squared is strictly greater than 4. If it was x squared plus y squared equals 4, then doing domains, we're only thinking xy plane. So just thinking not 3 variables. X squared plus y squared equals 4 is a circle. I meant to say ask you what it was, but I just told you. It's a circle of radius 2. So I have this circle of radius 2 that if it was equals, it's not equals, it's strictly greater than. So I'm going to draw a dotted line for that. And now because I have this inequality, either I have the outer bit outside or I have the inside. Do I want the radius to be bigger than 2 or less than 2? Good, so the x squared plus y squared is bigger than 4, which means my radius is going to be bigger than 2. So the domain is all of the stuff outside of this circle. So there's not going to be any function hanging out inside of the circle. It's all outside of the circle. Should we see what that function looks like a little quick? Let's do it. Where's my GeoGebra at? So if I put this function in, 1 divided by the square root of x squared, am I still up, plus y squared minus 4, we can see that this function, even if I zoom out, it's going to be approaching infinity as I hit that circle, and then it's going to have a huge gap in the middle. There's not going to be any function inside that circle there. So the domain is just those x values and y values. So that's sort of the graph of the domain if I look straight down at it. We see that? Okay. So I'll pop in this picture so we have it in the slides as well. Come on, move back over. Okay, so we got that. So let's do the final thing in this section is we want to match these functions and graphs. So we need to sort of pick out some things that we can notice about them that it's going to help us graph them. So we want to think about what happens along the axes. So along the x-axis, so when y equals 0 and z equals 0, along the y-axis, when x equals 0 and z equals 0. Oh, sorry, not z equals 0. I don't know what I was saying. We want to think about the z values along those. We can think about symmetry, especially rotational symmetry. We can think about sign, if it's positive or negative, in the different, I'm going to say quadrants because I'm just thinking about the domain here. And using that, and then I guess I can say overall shape and oscillations. Oscillations. If I use these properties, I should be able to kind of figure out what's going on. So let's start with just looking at that first function. Let me number these. 1, 2, 3, 4, 5, 6. Whenever you see an x squared plus y squared hanging out together in your function, and that's the only way that x and y appear, so they always appear squared and added together, that's what's going to give you that rotational symmetry. So that's like when you take a shape and you rotate it around that z-axis, that's where that x squared plus y squared comes in. So we saw that in the cone, z squared equals x squared plus y squared. We saw that in a paraboloid, z equals x squared plus y squared. And so for number 1, I have sine of square root of x squared plus y squared. So it should look like sort of sine of square root of x rotated around that z-axis. Does anyone see a graph that kind of looks like you took a sine wave and rotated it around the z-axis? B, can we see that sine wave rotated around? Now that square root inside there is gonna do like some weird things. In fact, because it actually is, it's squared and then square rooted, it really does just give you a sine wave rotated around. So this one is number 1. So this rotational symmetry, we're going to be looking for those x squared plus y squareds. Is there any other one that has exact rotational symmetry? Does anyone else see a rotational symmetry one? 4. So in the graphs, right? Sorry, no. In the functions is what you were saying. Okay. I do see an x squared plus y squared in the power of 4, but there's also an x and y squared that aren't added together. So it's going to have some symmetry, but it's also going to kind of mess up that symmetry. In 2, I'm seeing an x squared plus 4y squared, which is really close to a symmetry. And that's the one that I was thinking about as well. It's going to be like kind of, instead of a circle type symmetry, it should look more like a ellipse, because it's just like an ellipse. So it should be something that's sort of symmetric but stretched out a little bit in one of the directions. Do we see a graph that looks like that? Maybe F. And now let's think about it. It's 1 over that x squared plus 4y squared. So when x and y are big, the function should be small, because I'm dividing by a really big number. And when they're really small, it should be big. So then this is going to look like that graph number 2, because it's almost symmetric, except it has more of an ellipse there. It's small when x and y are big, and it's big when they're small. Because if you could divide by things smaller and smaller, the function gets bigger and bigger. In particular, what's the bad number to divide by? 0. So when x and y are both 0, it should blow up to infinity, which we're seeing along that z-axis there. Okay, so we sort of did our symmetry. Does anyone have sort of one that they want to focus on next? One that we like the shape of? How about between, well, these 3, what are we seeing that's kind of going on? They also have some amount of like oscillations, right? We're sort of going up and down in different ways. Which of these functions is probably going to have some oscillation to it? 3 and 6, because they both have that sign in there. So let's look at 3. it should have a sign x when y is constant, and it should have a sign y when x is constant. So I should be seeing those sine waves in sort of both directions. Is there a graph that looks like I'm kind of seeing sines in both directions? In D, can we see if we cut, all right, doing the traces, if I cut this way, I'm seeing some sine waves. And if I cut this way, I'm seeing some sine waves. And so I'm going to get those sine waves in both directions. So that's going to be 3. Okay, the other one that had the sine oscillation was 6. It had that sine squared term. So I should also be seeing some sine oscillation from that one. For that one, could it ever be negative? No, why not? Yeah, I've got a sine squared and then a quarter y squared. So both those quantities are squared and squared quantities are positive. So it's going to have some oscillation, but it's always going to be positive. So when x is constant, so sort of forget about the x term, the y should look like a parabola. And when y is constant, forget about the y term, the x should look like a sine squared. So I should be seeing some sines in one direction, and then I should be seeing parabolas in that other direction. So do we see how that looks like E there? Yeah, we okay with that one? Okay, so 6. So now we have 2 left. We've got this 4 and this 5 to narrow down. Let's think about maybe what happens along these axes. For this one, when x equals 0, what do I get? Well, I get e to the negative y squared, but it's times by 0. So it's just going to be 0. Just along the actual axis, not in the direction of that axis. And then when y equals 0, it's the same thing. So it should be 0 along that y-axis and 0 along that x-axis. I can sort of notice that both of them have that property-ish. It's kind of harder to see for A. It might be going up there. And then what about the signs in the different quadrants? Does the sign, the positive and negativeness of this function depend on if x and y are positive or negative? No, because e is always positive, and x squared is always positive, and y squared is always positive. So I got a bunch of positive numbers I'm multiplying together. So this function should always be strictly greater than or equal to 0. And so it can't be A, because A has got both positive and negativeness. And so we end up with it being C. So it does have the right stuff along the axes, and it also has the right positiveness. But we can also say, okay, when x and y get really, really big, you get e to a negative big number, which is close to 0, and that's why it's flattening out as you move away. When x and y are small enough, then the x squared, y squared out front sort of win, and that's going to pull up those different peaks in those quadrants. Okay, and so then like by process of elimination, we could say that this one has to be 5. Or we could say, okay, well, if I look at what happens along x equals 0, it should be 0. Along y equals 0, so that x-axis, I should be seeing a cubic function. Oh, no, yeah, y equals 0. I should be seeing an x cubed. So I should be seeing kind of a cubic function here. And then I just sort of have that both positiveness and negativeness that's going on. I've got the cubicness, and so we can kind of narrow that down. So you need to be able to use these different properties to identify these graphs. That's kind of the overall thing to do. Take time with these, practice. There's a couple different matching exercises in the book. There's some on the WebAssign. Try it. Graph it in GeoGebra. See how you did. Try it again later after you forgot what the GeoGebra graph looked like, right? Just keep going back and forth between trying to guess what it looks like and then seeing what it looks like in GeoGebra until you kind of can come up with some techniques that work for you. And we won't do a ton of things like this. Okay, let's move on. We want to explore